Okay, I'm actually Neil Spring. My advisor is David Wetherall. I'm a grad student at the University of Washington. It even works. Excellent. Okay, and over the past couple months, I've built a tool. It's kind of a toy for me. It's a lot of fun. And my goal here is kind of to share it with you and let you play around with it. The URL, if you want to start browsing around, is scriptroute.org. I work for David and Tom, as I said, at the University of Washington. Why are we doing this? We're building a distributed measurement platform under the premise that everyone out there measures the network, not just graduate students like myself, but also operators. Yeah. Into the mic more. Okay, sorry, I'm not used to this mic thing. But the problem is that network measurement itself is hard. We had, let's see if I can stick the mic between myself and my screen, maybe I'll talk into it. We had a project at UW called Rocket Fuel, and the goal with Rocket Fuel was to take all the public traceroute servers that we could find and have them run a carefully selected set of traceroutes through a handful of ISPs and use that to try to construct as accurate maps as we could of those 10 ISPs from no internal traffic, right? No OSPF feeds or anything. And we found that although this was really successful, this was also really very challenging. That is, it took a lot of graduate student time, my time, to try to care for and feed the machine so that we could get good measurements and deal with issues of strange servers and things like that. So the problem that we're trying to address is that doing this sort of distributed network measurement is hard. There's two pieces of it being hard. One is the development problem. That is, if you want to write your own tool or you want to change traceroute in some way, you have to deal with both kind of some arcane interfaces like calling set sock opt IP header include to get the socket to do what you want it to do. You need to have root, and any place I've ever been, if you want to have root, you have to administer your own machine from scratch because nobody wants to touch that machine. And then once you finally get a tool that might work, you have to then try to distribute it around, and that's, an order of magnitude harder just by virtue of being a distributed system. So we wanted to, after going off and building something that did all of this from scratch, we wanted to build an infrastructure that would make it easy to do again, taking all of the lessons that we had. So we built Scriptroute, which is an environment for distributed, lightweight, active network measurements. I would try to add more keywords there, but I would run out of space. Trying to simplify the development of these tools, we're using measurement scripts and not using some sort of SUID Perl thing. That would be disgusting. But expressing just the logic of the measurement in a script and using an amount of infrastructure there to generalize what all of these network measurement tools actually do. We've deployed this over 42 sites, so it depends on who has written a buggy kernel module and crashed a machine, on Planet Lab, which is an Intel-funded at the moment platform for deploying network services. So you can actually play around with this as it stands right now. Just to give you a sense of the context a little bit more, if we had our ideal network measurement platform, I realize this is not the ideal network measurement platform for everybody, but it would let us run any network measurement we wanted to. That is, anything that we could find on Kata's tools taxonomy page, for example, and we'd be able to run it from any host. And being able to run from any host means that if we're researchers, we could get comprehensive vantage points, not just what the internet looks like from research universities, or if we're trying to debug the network, we could get comprehensive coverage. That is, if our cable modem was down, we could ask our neighbor if their cable modem was working, or if it's just a maintenance outage because we're up really, really late at night. Obviously, we're not going to get here, right, because there are some pretty nasty tools on that taxonomy page, and we wouldn't want everybody running them everywhere. But maybe how close can we get? Trying to put some other stuff into context, you could think about doing something with a dedicated testbed like NIMI or RIPE-NCC or AMP or Surveyor or there are a bunch of these. These would let you run any measurement you could come up with and convince people to deploy, but their deployment is kind of limited by having to use dedicated machines and either uniform hardware or software image or special hardware for timestamping. So although these, the hardware for timestamping is getting cheaper and hardware is cheap and power is cheap, these are somewhat inherently limited in deployment. You can just install stuff on your own workstation. another extreme at the other end, where you could run stuff anywhere, but a very limited set of measurements, would be to use the public traceroute service like we did in rocket fuel. These are great, right? They're everywhere. Anybody can put up a server. Joe Sysadmin can put up a server, and Joe Sysadmin can query anybody else's server. And when we used almost 300 servers representing, almost 1,000 routers and vantage points throughout the internet when we did our study, but you can't do anything, right? You can only do traceroute, and traceroute kind of sucks for doing the sort of stuff that you might be interested in, right? It takes 3 packets per hop. That's not necessary all the time. It does reverse name lookups. Who really cares? You could do that at the client anyway. So we want to provide something that's a little bit more flexible. So Scriptroute is designed to support measurements that use few packets, few bytes. They're lightweight, that is. They send safe packets. You can send anything you want, but we're going to try to make up a rule set that defines what things we don't want you to send. So, for example, like IP broadcast packets, we wouldn't want people launching Smurf style stuff from here, or spoofing a source address, whatever. And they use little resources. That is, I don't think there are really any tools out there that do something very complicated with the responses that they get back, but there it is anyway. And we want to be able to do this on sort of shared ordinary servers, any Linux box you could find. And instead of using a uniform hardware image or a uniform complete software installation, we're using the interpreter that's interpreting these scripts as the environment. That is, you can expect the interpreter to be there and support roughly the same features. And so the goal then is to really just combine either the best or the worst attributes of both systems and get something that's also useful. So we've built a handful of tools, both local tools and distributed tools, and we have a handful of grad students in our networks class working on some other things. So it's been really fun. Just to review some of the things that we've built, we've re-implemented a handful of things, both traceroute and TCP traceroute, and it takes very little code, and I'll show you both of those just briefly in later slides. You can start staring at them now if you love code. We have like 3 implementations of ping just because it's so easy and fun. An implementation of ALI, which is a tool that we wrote in the Rocket Fuel project that's designed to take all of the interface IP addresses that come from traceroute and collapse them so that you find routers. That is, when you take a traceroute, you're actually seeing the list of ingress interfaces on these routers, and you'd really rather make a map essentially make a map or a graph of routers, not interfaces. That's not very helpful. We also implemented a tool called SProbe. Let's see if I can get some water here. SProbe is this tool for packet pair bandwidth estimation that was developed. Oh, there's the, yeah, okay. So SProbe is this tool that is kind of like NetTimer, if you know about that, for packet pair bandwidth estimation. Just another thing that we could throw in that was lightweight and fun. So although it was really easy to re-implement existing tools, is kind of the point, it's also really easy to compose these tools into something that's distributed, either for, and we've done 2 of these things. One was for GNP evaluation. This is like some researchy thing. Don't worry about it. Essentially all it means is that we decided to ping 8,000 hosts from the 33 servers that we had a couple months ago to try to build a data set that was bigger than the data set that the original paper used. That was fun. It only took a couple hours to run the pings. And then we also have built another tool that builds a reverse path tree, takes traceroutes, takes the alias resolution thing, and builds a tree. And I'm going to show that to you a little bit more now in pictures. So you can kind of see what's going on. This is a tree of paths from all of the Planet Lab servers that we had a month ago to my desktop machine. And my desktop machine is on a research network, and most of those Planet Lab servers are on research networks, so most of the routes go across Abilene. That's some of the stuff on the right. The thing that I wanted to point out with this description is that it's reasonably easy to run these sorts of distributed active measurement programs, and we actually have some kind of cool tricks here, and that this is not just traceroute. This is traceroute as a tool plus alias resolution, and we do we've perturbed traceroute in some interesting way that means that once a path hits a piece of the tree that's already been traversed, it stops, it's done. It doesn't have to waste the time going all the way to the destination. So I'm going to zoom in a little bit and focus on the route. Okay, you might be able to read this, I'm not sure. In the upper right, I just want to call attention to a couple things, is the Seattle router on Abilene. We actually see two of its interfaces, one that goes to Denver and one that goes to Sunnyvale, and it's at a merging point of two pieces of the tree. So these things are aliases and they're listed together. The line thickness is trying to give the impression that there's a tree, right, with a trunk and branches and stuff. So that's kind of fun. And somewhere in the middle, there are a handful of IP addresses with pluses next to them. As you know, traceroute doesn't go everywhere in the network, so these are unresponsive successors to a previous IP address. That is, you saw an IP address in the traceroute, and then the next few hops you would ordinarily see stars, and then eventually get to someplace, and those are just placeholders for those stars. If you want to play, there's a URL. Now, it takes like 5 minutes to generate one of these things, and they run sequentially. So if you all jump on it right now, you're not going to see anything until like tomorrow or something. So be nice, or look at some of the ones that are already generated first before you decide that you want to create your own. But it's fun. I encourage you to do that. So just to kind of reinforce things, we were able to use the flexibility to make this tool very efficient. That is, we could do all the name lookups with the client, wouldn't have to pollute everyone's name cache. We don't have to retrace the tree. We don't have to take more than one probe per hop like we would if we were using ordinary public traceroute servers. We could, and what that means is that we get 195 traceroute packets instead of 975. I gave this talk to Ratul, and he said that you guys would really like the numbers. So that line is there to appease you. It took. For that particular tree, it took 1.5 minutes of tracing and 2.5 minutes for alias resolution. If you end up tracing to someplace that's not responsive, it takes much longer. So just so you know if you're intending to play. And more importantly than just being able to do this, we think of it as the foundation for additional tools. That is, to take these trees and annotate them with link properties. There's actually the version that's ordinarily generated is annotated with latency, but it's latency done foolishly based on the difference in RTTs from the traceroute probes. We could also try to group by service provider or render on a world map. Kata has tools for doing both of those. So it'd be fun to play around with that stuff. These graphs are rendered by DOT, which is part of the graph there's package from AT&T, which I absolutely adore. It's so cool. Makes things so easy. And one of the things that motivated this was that when we talked to our own communications people, one of them suggested that that a useful distributed measurement tool would be one that would find servers that share paths so that you could infer which link was misbehaving, which link was being a problem by collecting a handful of servers out there and figuring out that these guys don't have any problem and these guys do, and they share this particular link whereas these other ones don't. So we think that we can build on this and make something useful. To give you a sense of what's underneath the hood, this is a cartoon version of the architecture. A client interested in making a measurement makes a query to the DNS. We have our list of active servers in there, listed by AS or by country. So if you wanted to get a traceroute server or a scriptroute server, that is in AS 73, which is UW, you could query for that. Then contact a front-end web server, which just does some handful of things to make sure that you set up your TCP connection correctly and pass across a script. It hands the script off to an interpreter. The interpreter runs in a resource-limited Scriptroute sandbox in safe mode, all the fun keywords that you can string together. And it hands off packets that should be sent out, probe packets that should be sent out to the core. The core is going to deal with opening up the raw sockets and opening up live PCAP, and then restricting access to the network, so enforcing any policy that we want about rate limiting or filtering of packets. It also deals with matching the responses to the sent out probes, so it makes that very easy, and hands back the responses to the interpreter. The interpreter can do whatever it wants, print out some stuff to go back across the network. We chose to express these measurement scripts in a language called Ruby. It is object-oriented, type-safe, general-purpose scripting language. It has a safe mode that prevents system calls. It integrates very easily with C, and I understand it's all the rage in Japan. That should be motivation enough. We then took the interpreter and enhanced it with a handful of things. A send train call is what's used to send out a handful of probes, possibly spaced out with some intervals. Collects responses, returns the responses as an array. And also include packet types, your various ICMP constants. Do network byte order conversion, automatically convert string-based IP addresses to their binary form, or do name lookups if necessary. And ultimately, the core is going to deal with checksums, matching responses, stamping the source address, dealing with policy, making things just very, very easy to write and express. And just to give you a sense of just how brutally easy it is, or how much you can concentrate on actually expressing the logic of a measurement, did a couple of code samples. I don't actually expect you to read this because it's a language that you probably don't know, although it's reasonably simple and you can stare at it all you want, either in the slides or in the manual, which goes line by line and describes what's going on. Essentially, this is traceroute, creates a new UDP packet, sets the destination to a command line argument, loops for 64 hops, 3 repetitions per hop, waiting for a port unreachable message, printing out the latency. As you know, that's exactly what traceroute does, and that's exactly what this does. Now, if we wanted to modify this, right, in any way, I'm going to modify it so that it does TCP traceroute, sends TCP packets instead. It's actually very simple. It's part of the goal. I've highlighted in red all of the things that you would have to change, right? You would have to create TCP packets instead of UDP packets, wait for TCP reset instead of an ICMP port unreachable message. Just a little bit of extra logic. So our security model, it's actually the thing that you have to worry about is, we're moving scripts around. The thing that you have to worry about is security. So I'm going to describe it in two pieces. One is about protecting the hosts. We use the interpreter in safe mode, so it has restricted access to system calls to begin with. It runs as nobody inside the chroot under kernel resource limits that limit its memory footprint, its CPU time, and then also the duration of the script execution is limited to like half a minute, and the number of scripts that execute concurrently is also limited. So the host is pretty well safeguarded against code that even if it wanted to be malicious couldn't. Then you have to worry about what packets get sent out and how fast they get sent out to protect the network. And we have rate limits on per byte, per packet, and because I believe that SYN packets have absolutely no utility in network measurement, we aggressively limit those to a very small rate. We're also going to filter out bad traffic like broadcast frames or fragments or anything like that. Prevent source spoofing by stamping the outgoing source address. There's also, in the architecture, a facility for destination-specific filters. That is, if somebody really doesn't like getting measurement traffic, like I understand that there are some, you can set up a filter that would be consulted before generating traffic out to those addresses. And finally, there's a facility for logging the sent packets on behalf of whoever asked for them, and whoever asked for them presumably had to set up a TCP connection, so it's pretty obvious who at least by IP address, asked for the measurement. So it doesn't provide anonymous reflection. Just to give you, why not? This is our name tree, just to make it a little bit concrete. If you were to look up 73.as.servers.scriptroute.org, that would give you a list of DNS round robinable Scriptroute servers in AS73. AS73 is the University of Washington, not an actual transit provider or anything like that. You could also look up by things in North America or in the United States or any, just arbitrarily chosen. We also use this as a database for storing that destination-specific filtering policy. So finally, I hope I've kind of expressed that the system is flexible, that it is, in terms of being able to execute scripts remotely, these scripts that encapsulate network measurement logic, that it's safe and that the script's behavior and the packets that are sent are limited. It's open in that users are essentially unauthenticated. They're logged, but there's no credential system involved, and anyone can run a server. We have a facility for local control that is the administrators control all of those limits that I mentioned on 2 slides ago, which packets can get sent. Could, I guess, loosen up the requirements if they wanted to, but whatever. It is a single system as opposed to anything that would require a manually maintained list in HTML, that the servers are listed in DNS, and you have the ability to easily distribute measurements across all those servers. We have an alpha deployment on Planet Lab, planet-lab.org, not, the dash is important, I guess, that I'd like for people to play around with and see if it's, in addition to being fun for me, useful for someone else. We have source and packages and a couple of manuals and a draft paper and these slides all at scriptroute.org. And that is the end of my talk. Thank you.
Would you be able to use the system to play with IP options or TCP options on packets and see if they would be carried with those options across particular networks?
So you could use the system, but I would have to modify it. My packet classes are very basic, and they don't have any facility for throwing TCP options or manipulating the data portion of the packet. Flags, yes. TCP options, no. It'd be an interesting feature to work on, though. Yes.
Is there any kind of rate limiting worked into this?
Yes. We rate limit by
I missed that. Sorry.
Byte-wise. Sorry, I must have skipped it. Per packet, and just to encourage people not to use SYNs by how many SYN packets get sent by any experiment. The architecture is one where we don't want to have any centralized control deciding, which experiments get to go off. So we have to make sure that even in the presence of a widely distributed system, each of the experiments themselves is safe or unlikely to generate a lot of traffic, even if all of them were doing roughly the same thing. So the rate limits are very important. Okay. Thank you.